turn around, and the R will just keep going all the way out. And as I said this morning, by just looking at the spectrum and seeing which branch is actually forming the head, you almost immediately have information as to where the upper state is located relative to the lower state. You can immediately say if R branches are forming the heads, well, the upper state is out. If the P branch is forming the head, upper state is in. But immediately you also know what you have done with the electron. In one case, you have gone from bonding to anti-bonding, maybe. The other case, you have gone from anti-bonding to bonding. You can actually start talking about what sort of orbitals you have excited, where you put the electron and so on, by simply figuring out whether the R branch forms the head or the P branch forms the head. This is probably the crudest conclusions you can get. By analyzing the spectra, you get a lot more information. But even if you didn't go into the depth of the analysis, you straight away get information about the molecular orbital excitation that you have actually excited in that particular transition. That's the sort of information you can get by simply looking at where the heads are actually formed. So in any given spectrum, you will see either P branch forms the head or R branch forms the head. I'll just show you some more spectra. This is only to show you that the B prime is only approximately equal to the prime. It's not very different. So what do you think will happen? They all stay like nearly equal. They're not backing up, and the intensity is already dropping off. So which means, in this case, the head might be forming somewhere over here, but I can't even get there because the intensity is already gone. I've run out of population before I can see the head formation. And this is something that you will see in vibration rotation spectrum. But the head formation is actually very, very dominant or very prominent when you're looking at electronic spectroscopy, simply because the B values can be extremely large because the two electronic states can be quite different in the equilibrium internuclear distances. And of course, the other one is the other one. In the limit when B prime and B double prime are nearly equal, what happens? Equal spacing on both sides. You're not going to have a pattern of lines, and therefore you will not even see a head formation, which is what happens in rotation spectroscopy. So you go from rotations to vibrations. There's a small complication that you throw in, but by the time you get electronic spectroscopy, you have thrown in a lot more complications, and you start seeing new phenomena. Bandhead is not a phenomenon you will see in rotation spectroscopy. Bandhead is not likely to be a phenomenon you will see in vibration rotation spectrum. But bandhead is a phenomenon you are likely to see almost always in electronic spectroscopy. Let me show this. Just to show you a few spectra. This is a typical spectrum that you will see. This is copper hydride, CuH. And of course, these are species produced in the discharge. So don't ask me about, copper valency 2 and this and so on and so forth. It's not the most stable valency. In a discharge, you will see all sorts of species. And therefore, this is copper hydride, the diatomic, and this is a spectrum. And you can see, here's my R10, and it goes off on the head and starts to come back. And the P actually starts marching off in that direction. And you will also see that at some point over here, you may actually have P lines and the R line in the same place. And therefore, you will have a tough time really. But then it's not really that bad because there are two things you can do to check out whether this is a P line or an R line. First, intensity. Where P is marching off, what's the R actually? The R is a line that has gone all the way out and then back. So it has to belong to high J's. If it is high J, the intensity must be smaller. Therefore, if you have small intensity sitting in there, then you know it's one of those branches that has actually taken a turn and come back. So if that's P, then R must be the ones with very small intensities. Pardon? That's the outer over there, R, that's a mistake. R20, actually P50, you made a mistake of it. So the R actually starts off over here and comes back. And of course, the P1 is smaller than P5, but that's understandable because the intensity actually go up and then start to come off. But see what else happens. You have some crosses out here. The cross here, the cross here, cross here, which actually reasonably intense crosses. These are impurities. So as if the analysis of the P branch and R branch is not complicated enough, very often in the spectrum, you might also have impurities which are contributing to spectral features in the same region. And therefore, you have to figure out whether it's an impurity peak, whether it's a P branch, whether it's an R branch, and in some cases, you may have even other branches, and therefore, electronic spectral assignments can actually be quite complicated. Of course, I will know this is an impurity peak by doing a set of experiments such as changing the sample. If I use copper hydride to a certain source, use a different source and see whether the impurity peak still remains. Or do isotopic analysis and so on. And then you will be able to figure out whether the peak that you're seeing there actually belongs to copper hydride or to something else. This is again copper hydride another transition where again he has shown all these. Look at this one. This is an aluminum hydride transition. And you can see this very strong intensity over here. Actually, it's again an impurity. But again, you have to figure out that that's an impurity. So, assigning rotational lines in electronic spectroscopy is not the easiest. It's actually a very tricky, very complicated issue. But the sort of data that you get is absolutely wonderful because you get precise information about electronic states, you get precise information about the structure of the molecules into electronic states and so on. You can see that there is an R head that formed here. So that is everything about Q. What is Q? Delta J equal to 0. All the while I kept telling you delta J equal to plus 1. I didn't want to complicate it. But there are molecules that can show delta J equal to 0. And when they show that, what happens? You have a P branch, an R branch, you have a Q branch, and you have the impurity peaks. So you can see how complicated things can actually get. But, as I said, the more branches you have, the more lines you have, the more information you get. And therefore, while it is hard on the one hand, you have to assign all these. But when you do assign them, the sort of information that you can get about the electronic state is actually quite precise. And that's basically what I want to show you. So what we have essentially done is, whatever we learned in rotation spectroscopy, whatever we learned in vibration rotation spectroscopy, we have simply just assigned them to electronic spectroscopy. But with the added information that in electronic spectroscopy, you can have B prime and B double prime. It's very, very different. And they are very different. It is not just a simple extension, it actually gives rise to a new set of features, a new set of information that you can actually get from the whole spectrum. And that's the reason why in electronic spectroscopy, you start getting information about the P values for the various states quite accurately by simply doing a rotational analysis. Okay. Now let's see how the vibration thing pans out. And there we will go to, what are the selection rules for rotation? Is delta J equals plus minus 1. I'm not going to bother you with delta J equal to 0. Molecules can show that. But we'll still stick to our simple version of delta J equals plus minus 1, which was true in the case of rotation spectroscopy, which was true in the case of vibration spectroscopy, going from one vibration level to another vibration level. And I'm now going to insist it's true for electronic spectroscopy when you're going from one electronic state to an entirely different electronic state. There are molecules that can show you delta J equal to 0, and we call that as the Q branch, but apart from knowing that such a possibility exists, don't bother yourself more with that information. We will keep sticking and learning about what happens if delta J equals plus minus 1, which is what we did. One gives you a P branch, the other one gives you an R branch. Of course, in Raman, we saw it means plus minus 2, and of course, then it's an O branch and an S branch. Raman can also give you delta J equal to 0, which would be the Q branch. So you can have O, P, Q, R, S. And those are the branches we are dealing with. But as far as this course is concerned, as far as the molecule that we are looking at is concerned, delta J equal to plus minus 1 is sufficient to know how to analyze them or how to draw information out of them. It's enough if we know that delta J equal to 0 is a possibility in some molecules and which will give rise to Q branches. But beyond that, we will not worry about the analysis of a Q branch as far as this course is concerned. So this is still a selection rule that's strictly obeyed in electronic transitions. It's obeyed in rotations, it's obeyed in vibrations, and it's obeyed in electronic transitions. So if I give you a bunch of electronic states and I ask you to draw me some transitions between states, keep in mind you have to draw me lines which will connect delta J's which are differing by 1 quantum. 4 can go to 5 or 4 can go to 3, but 4 can't go to 6 or 4 can't go to 7 and so on. So the delta J equal to plus minus 1 selection rule is going to be obeyed in rotations, vibrations, and in electronics. What are the selection rules for vibrations in the vibration spectrum? Delta B equals plus minus 1. But when is it true? Strictly true? Harmonic oscillator. The moment the oscillator becomes an harmonic, what happens? You can have plus minus 2, plus minus 3, plus minus 4, and which we call as the overtones. So this is the fundamental. In addition to the fundamental, I can have overtones. It's an essential transitions from 0 to 2, 0 to 3, and so on. But since these transitions have basically grown out of a relaxation, okay, you have it. Their intensities are not very great. And the only reason they even happen is because the curve, the potential is being parabolic, which is your true harmonic oscillator potential. The potential has actually played out. So this would have been a delta B equals plus minus 1 selection rule. Harmonic oscillator has to obey delta B equals plus minus 1. But we know no oscillator is truly harmonic. There's always an harmonicity. And when this curve becomes like this, the other transitions like delta T equals plus minus 2, plus minus 3, plus minus 4, all of them become possible, albeit with small intensities, not large intensities. The fundamental will still be strong, but these are not disallowed. Generally, their propensity is very small. That's basically what it is. So, this is going to be the strongest, everything else is going to be weak. So that's something we learned in vibrational rotational spectroscopy. The question now is, what happens in electronic spectroscopy? And what's the question I'm asking myself? The question I'm asking myself is the following. Let's say I have a curve here. And what should I call this curve with the ground state? X. Let's get that. So that you now pretend to be professional spectroscopists. We label the ground state as X states. And let's say there's a state out here. And let me call this as an A state. So I'm basically looking at a transition from X to A. What A is, we will get to that later. As of now, all we need to know is the ground state, with the ground electronic configuration, an excited state, and the molecule is making a jump from X to A, in which what I'm essentially doing is pulling out the electron from one molecular orbital and putting it somewhere else. That's basically what I'm doing. But the moment I do, this new potential curve comes into play, and once the molecule is in this state, with the electron now sitting in a different orbital, the molecule has to vibrate as per the tenets of this potential. The question now is, I go from here, into what vibration level should I go into this? If I do this, what is my change in vibrational quantum? Delta V is 0. So if you thought that rotations had a certain pattern, what I learned in rotation spectroscopy seemed to obey in vibration, seemed to obey in electronic. Now, does that mean what I have learned in vibration spectroscopy with respect to changes in the vibration quantum number, which is delta V equals plus minus 1, will that be okay here? Which means that starting from 0, I shouldn't go to 0, because that tells me this plus minus 1. Therefore, the question I'm going to ask myself is, how do I decide, starting from a given vibration level, which vibration level I go up in the excited state? In other words, what are the selection rules for vibrational transitions between two electronic states? That's the question I'm asking myself. If it's a pure vibration spectrum, meaning I'm making transitions from here to here, here, and so on, we know that, delta V equals plus minus 1. But when I'm jumping from one electronic state to a completely different electronic state, what is my selection rule? Do I still have to stick with this delta V equals plus minus 1 selection rule for a harmonic oscillator, and then anything else goes for an anharmonic oscillator? That's the question. By the end of the class, we will look at the quantum mechanical picture, but this is the question that plagued most people at that point in time. Because when they actually did the experiment, there seemed to be no method in the madness. Because some molecules, you will see transitions going from 0 to 0, meaning this is by V double prime, this is V prime. This is an absorption process. So I am going from the lower state to the upper state. There were molecules which showed that from the lower state of V double prime equal to 0, you are going to be equal to V prime equal to 0, you are going to V prime equal to 1 and 2 and nothing else afterwards. There were molecules in which you started from 0, you didn't see 0, you didn't see 1, you didn't see 2, and maybe you started seeing 0 to 10, 0 to 11, 0 to 12 and so on. There were yet some other molecules where you started from 0 and saw 0 to 20, 21, 22, 23 and so on, but none of the others. So it almost looked like there seemed to be no method at all, or no selection rules even, that was prevalent as far as making transitions from one electronic state to another is concerned. If we just had to slap the selection rule that we learned in vibration onto this, what should that be? Delta V equals plus minus 1. But it didn't seem like we were doing that. Some molecules showed this sort of behavior, some showed this behavior, some showed something else, and all sorts of complicated behavior. It just didn't seem to have a specific selection rule as far as vibration transitions between electronic states were concerned. And that is when our good friend Frank came up. And I think somebody's birthday